Good morning, guys. I'm Subraiz. I'm a part of the member of technical staff at Perceptron. And the talk I wanted to give today is about using VLMs in a larger system. So to go from more of a one-shot approach into deliberate vision. And what this kind of looks like is kind of going from a can it find like anything approach to more of can it reliably find everything? And just over here, you can see like we have a tray with a whole bunch of like nuts and bolts. And this is kind of the image I'll be working around for the rest of this presentation. Um, some stuff might be at a bit higher level, but if there are any, I guess, more technical questions, I'll do my best to answer them as well. But yeah, let's move on to the first slide. So the normal way to kind of build factory inspection is kind of a fixed pipeline. You have the taxonomy and like you define the fixed classes, you have the data, you could fine tune a YOLO model and then it deploys. And this is great when the problem size is known, you know exactly what you are looking for. But when stuff like open vocabulary is needed, this is kind of where we move towards more of a this VLM approach, where we actually give it a prompt image and some visual examples, whether that's positive or negative exemplars, and then we get a response back. Now, one key thing is that this kind of does stop at this first evaluation. So it's kind of difficult to answer some questions, such as in the last slide, where you might want to find every nut and bolt, which, some of them might be clustered together, some of them might be overlapping. So we want to pretty much explore how does deliberate vision solve this. What we at Perceptron have been playing around with is kind of this detect agentic harness. So some of the stuff I'll talk about will be specific to that, but I think a lot of the learnings here can also be applied in your own setting. And there's basically like three main operating lanes we'll kind of be focused on. One is like again your traditional YOLO models. The second is just like a traditional VLM call, and then the third is this deliberate vision. So just because with VLMs we do have like this open vocabulary concept, the flexibility around that does not actually guarantee, completeness. There are three ways to attack the same task. One is in that specialized manner. You have a trained model that's fine-tuned for this. This is kind of like, I guess, what I would say the lowest bar. It's practical for stable, high volume work, especially in any area where latency is very important. Then again, I'm just coming back to this term again. We have deliberate vision, where maybe latency in this case isn't as important, but the cost or price of a miss or a false positive is much higher to the point where it would be preferred over something like a YOLO model. And if we just take this image, for example, different modes are going to have different failure cases where you might have some tiny pixels around the edges. The dense clusters I've noticed result in a lot of failure cases. You could have some pieces which are hidden and another piece which our base model actually struggled with a decent bit is when you have these similar looking pieces where you'll see some of these bolts have a missing washer and some of them do. And again, depending on like the cost of actually not detecting this, it could be worth it to go for this more deliberate vision approach. So this is kind of a very high level overview of how our detect harness works. But again, I'll go into more detail a bit more into this presentation on how this can also be applied in your own systems. So with us, it's a request that comes in with an image as well as any categories that want to be detected into a public endpoint. Behind that boundary is a harness. It's not a freely autonomous model, and it runs in a finite set of full images and crop observations. Every crop we have gets mapped back to the original image and merged into one result. And what you get back are detections, and along with detections, you also receive instrumentation if you want to do any logging for your workflow. And then in that bottom layer application policy, everything here kind of sits, everything in this span kind of sits outside this model. This might include stuff like acceptance, a human review, any kind of further validation that needs to be done. So let's dive a bit deeper into, I guess, like at a high level, how our harness kind of works. So the first is just a multi-pass repeated full image observations, building up broad evidence across the entire image. So basically, there's just more chances to look at the same image, and these are not independent ground truths. The second phase, routing, this is where, you could also, instead of just routing to the same one model, you could also do some like have some logic here to essentially say, hey, based off the size of this problem, can we just, pass this straight to a YOLO model? Should we, do like a two-stage detection, or should we kind of continue on with this VLM approach? Routing for us over here looks a bit different, but this is kind of a more of like an abstract concept over here. It's kind of more based on what the company's goals are. For us, afterwards, we move into this reinspect phase where we'll basically tile the image. And then if there are any tiles which need to be further zoomed in on, we'll basically split those up into tiles as well, and then perform our detections. And since we are tiling, tiles do overlap as well. So there is a stage after to reconcile and deduplicate any results that we see from the model. And then finally, we do return the final set of detections. So let's just walk through that same example with the actual tray image I showed earlier. So we have the broad observations here, which will just essentially be taking in that full image, breaking it up into grids and tiles, focusing in on specific areas, and then you can see where there's a cluster and some hidden pieces, it might choose to subdivide that even further. Um, and then finally, actually deduplicate and reconcile into the final result. And one second, let me move on here. Okay. So I think one important thing to mention is the reliability kind of comes from making sure that you are properly handling your failure cases more so than how good, I guess, like your golden set looks like. So if the risk or a failure case is omission, then the control is repeated coverage. So being able to actually, do what we did in this broad observations phase and span out and pretty much just have more eyes on this image. If the issue is with like tiny or dense evidence, then what we would do is we would overlap the tiles with higher resolution coverage. So now there are essentially more spots for us to actually pick the right object, and then later we can deduplicate it. However, if the issue is also with the crops that we are getting from the tiles, they are producing duplicate or clip geometry, then over here the control is like source coordinate reconciliation, and there's a bunch of like a lot of open source stuff out there as well, which handles this kind of stuff pretty easily. And finally, if you do need to like know what the run actually did, from our detect endpoint, we do provide workflow instrumentation as well, so you can go through logging. One thing I do want to note is there isn't a field such as a confidence score. So if that's something people are looking for, I think maybe sticking to a traditional YOLO model and getting a confidence score would be more helpful. But we do provide some sort of like workflow instrumentation for you to go through. And then finally, the last phase is kind of stuff that sits outside this harness boundary, which is again, maybe this is like a human review. This kind of sits more at the application layer. So these are just some benchmarks I wanted to share as well from the Dota V1 benchmark, pretty much covering a lot of aerial imagery and detections in there. When we tested it out with just our base Mark 1 model, meaning we were just making a request to our V1 shot completions endpoint, um, we're at 38.1, and then actually passing it through our agentic detection harness, we were able to get that up to 81.9. In fact, like a lot of the images generated here, at first I tried to just like manually draw them in, and I'm like, oh, what am I doing? I'll just save so much more time if I actually just give Codex access to our MCP server and have it generate the image. So a lot of the images you see here are also tested with our agentic harness. So, how would you actually test this if you're thinking about implementing it into your application layer? I think the first step is to just actually build that like golden set, just like normal operation plus any difficult conditions, and then actually like run those three operating lanes against it. What we kind of talked about, whether that's just some fine-tuned YOLO model um, just directly to a VLM and then maybe also through a harness and then actually having quality gates to measure against. And then it's important to measure more than just precision and recall. Localization error matters a lot more when the geometry drives an action. And again, depending on the price and cost of you actually having a miss or a false positive, this is a quality gate that could be very important to not miss. And then we also have slice gates over here. So we do provide instrumentation at the end of the request to actually see how images were tiled and cropped into. So also taking a look at that to make sure this is hitting the mark with whichever image you're supplying. And then, of course, like operating gates, and this is more about like, hey, how does latency matter over here? If latency, again, is a huge, huge priority, then yeah, oftentimes a fine-tuned YOLO model is going to win. And again, one thing I do want to reiterate, the purpose of this isn't to argue that one method is better than the other. Each method does have its own distinct purpose, and sometimes a hybrid combination of multiple methods provides the best outcome. So this is more just about like actually scaling and serving workloads. This is probably just left over from a previous presentation, so I won't spend too much time on this. We can just pass through here. But I do want to go beyond just categories. We do also accept positive and negative exemplars. So you can see in this image over here, there are some of these bolts which don't have a washer. So you are able to actually just pass in a negative exemplar and then provide two golden examples, these positive exemplars over here. And yeah, the detect harness or deliberate vision does pretty good, and it especially shines if you are able to pass in exemplars rather than just categories. So another cool thing is you can kind of almost use this in reverse to the point where you can gather evidence from the harness itself and then use that evidence as a positive or negative exemplar. So if you do want to say, hey, I want to avoid any, or you could just start with saying find all bolts that don't have a washer. And then based off that, you can actually sample that to pass into the detect harness. And this works pretty well in more like automated workflows where, again, maybe the problem size isn't known at first. So these categories could be more, I guess, like generalized to whatever workflow is running. So instead, you could have some system which like kind of points out anomalies. You could have our detect harness actually find those anomalies and then pass those back in as evidence. Okay, so let's talk about, I guess, kind of evaluating if this, deliberate vision concept is actually necessary, or maybe if just, these fine-tuned detectors are good enough. So the recommendation is kind of deliberately conservative. We do want to just preserve what already works. So again, if latency is important and a fine-tuned model is already working great for you, and it's also, it's giving you a much lower cost, then that's the bar you should be at. And, you can kind of just stop right there. But if there are higher price or higher costs to actually having a miss or having these failure cases, that's when you might want to consider something, like a VLM or a harness built around a VLM. So you do want to kind of price in one decision. What does this miss cost to you? What does a false alarm cost? And then also, what does this cost downstream? Like, is there added labor if there is a missed cost at this stage? And building a, golden set around your real failure slices and comparing that against all three operating lanes, which we've kind of been talking about over here. And I think, again, the most important thing here is focusing on those failure slices and adjusting from there. And you can just be running a shadow test alongside to actually see which systems are passing those gates that we discussed earlier and which ones are failing. And again, so I think the main thing which got kind of brought up at the beginning as well, find anything is a new capability, especially with like open vocabulary. It's really easy to just give a VLM an image and just say, hey, find everything you can. But finding everything reliably is still kind of a system design problem, and it usually involves having some VLM sit in a harness and have some kind of, whether that's like a detection loop going back and forth or just some system that's actually building on top of the VLM.